Hello everyone, nice to meet you. This is your dear loved engineer Cody. Um, I'm a software engineer and at the same time I'm also a lot into CAE, so a computer-aided engineering. I love simulation, and in this video I want to brag a little bit about my newest library and explain it to you. It can be found on GitHub. It's a Python library, currently covers LS-Dyna results. And you can simply Google it, or like I said, find it on GitHub. And it's meant that you get your data out of your simulation files without any commercial tools at all. I don't like commercial environments too much because, of course, we spend a lot of money so that they get better. That's the good part. The bad part is sometimes you cannot access your data very comfortable. And I think it's even more disastrous in the field of simulation, that it's very uncomfortable handling data, in contrast to informatics in general. So if you find this library and you want to install it to get your data out of a D3plot or a binout, go into this dist folder. Here you can find Python wheels pre-compiled with everything. I can even read femzip compressed files directly. So I put a lot of effort into this. Now, the functionality of the library, there is a helper file here. You can find everything you need, like here are the shortcuts for all the functionality. You can scroll down, the average stuff and tutorials and a billion million text lines with examples. But that's not why I'm here today. I want to show you it directly. So the most easiest thing, of course, in order to get started, is first going into the folder, of course, where I have my library test files. Okay, very nice. Now let's start an interactive Python console, and no, let's import it from let's import it directly. And here we go. Let's start with the D3plot. Now, you can simply invoke it with, you just give in the file, and that's all. Like, now the file is already read. It's a very small one. Sometimes it can take a few seconds because simulation data might be big. And now you have a lot of functionality, like you have basically three entities you want to think about. You want to, for example, get a certain node in the simulation. And what you can do is you can get, for example, its coordinates, and you get it like you have direct access to all the data, or almost all the data. I'm sometimes a little bit lazy. I don't implement what I don't need, but or what I think is pretty rare. You can also get any element, and therefore, but you have to specify the type first, and then the element ID. And it shall be mentioned that, you have to mention this type, because in LS-Dyna the IDs here are not unique. You can have a beam element with ID 1, 2, which I don't know why anyone in this world wants to do this, but it's pretty nasty when you're programming and you have double IDs. It killed me once in the beginning. I didn't know that. Nonetheless, so you can also get the coordinates of, for example, the element. Now, there is a problem when you want to get state data. Okay, so you want to get some state data, like the plastic strain of the element, and you see it's empty, and you're like, what the heck is going on? Like, there must be state data. Okay, so the real problem is that in the background, the file, it's same in like in a post processor, doesn't load what it doesn't need. You have to tell the library what it shall be loading, and of course we want to load the plastic strain for the shell elements, and max means you have plastic strain for every integration layer in shell elements, so you must deal with it. Either you mean it or you max it. For plastic strain, of course, usually you take the max of the plastic strain. And the really funny thing is, now if you make the get, okay, you get here one value only because there is only a single state in this file. It is simply for debugging and test purposes. Therefore, let's start a new, more serious files, and this one is compressed with femzip, so I need to decompress it during reading. And what we can also do is we can directly, in the first time when we read in data, we can parse and read the plastic strain, for example, and also, which is recommended, the displacement. And so you get like the displacement of the whole nodes, and the plastic strain is for the elements. Now it's reading for a few seconds. It takes a little while because it's a lot of data in this simulation model. And now we can do the same stuff like before. We can, I don't know, get any node. Let's take a node with index 10, and we can, for example, get its displacement vector, and you see, okay, yeah, what the heck is this? It's a vector with the length 34, which is the time, and the width 3, which is x, y, z. So it's currently working pretty well. Now let's get back to the element stuff. Let's get an element and get the plastic strain, and you can see, okay, really cool, you get the plastic strain directly. This is pretty neat functionality in my sense. You can access a lot of data like history values and stuff like that. I don't want to get deeply into it, but just think about, you get your element you want and you do with it what you want, and at the same time, like with nodes. You can also get, I like Pythonic stuff, like you can get multiple elements if you give here just a list, and what you get back is you get a list of multiple elements, and you can parse them. It's the same with nodes, by the way. And the last functionality or entity is a part. So you can get from your D3plot part. Here, let's get it. You can get, of course, its name in the file. This is some shell. And of course, you can also do, like for the whole D3plot, you can do get all elements of this part or whatever. Yeah, so it's pretty comfortable, it's straightforward. Look into the guide if you need something specific, like getting from a part its nodes or whatever, or from the D3plot only the shell elements. It's everything documented so far. Okay. Now, there's still one thing which was tormenting me for a very long time. It was plotting. Because plotting, we all know those models can be big. It's really, really difficult taking the right engine. It must be OpenGL accelerated. And a friend of mine, Taoli so far, he said, hey, why don't you do it in a browser? You know, a browser has WebGL and everything. And I was like, seriously? This will work out? And he was like, yeah, of course. And he showed me, and it was really nice. So what you can do is, for example, we have here this part entity, and you can simply write part.plot. And what it will make is it writes your part directly and into a temporary file and opens it with the browser. Like, this is the part I was bragging about. And of course, we can do this with any part. You can even do this with the whole D3plot. Let's start with the whole, maybe, because it makes more sense, because this is the full model. So this is the full model, and now comes the funny stuff. The cool thing is you can take this HTML and you can send it to anyone. There's no dependency, everything is embedded into it, and for models like this size, it has maybe 1.5 megabytes. It's really, really small, and even for a whole car, if you take out the parts you want, it's really not an issue. In size, it doesn't matter at all. Okay, so we want to watch it at a different time step. So let's say, okay, I want to plot it at time step 25. And here we are. You get the whole deformation, like in a post-processor. It's really, really funny how well this is working out. But now someone might say, yeah, I want some results. So I made some predefined results. You can, for example, call the plastic strain directly, and what it will do is it opens the model with the plastic strain, which you can see here. Okay, so pretty awesome. You have already fringes, but this scale here of the fringe bar, it is not really nice. So there's the argument fringe bounds. Oh, that was wrong. Fringe bounds equals, let's do it between 0 and 5%. Ah, browns. No, browns don't exist. That's not recommended at all. Okay. The model opens, and here we go. This is like the same model as before, but with different fringe bounds. So this is pretty much the same as this one. There is still a lot of stuff you can do. For example, you can, and this is my most favorite, let's say you want to have time step 0, but we want to plot the fringe from time step 25. And what you can do is you can define an arbitrary function, like a lambda, and what it does is it takes in an element and returns or must return a float, a value. And in my step here, of course, I take the plastic strain at the last time step. Okay. Oh no, that is not right. What is wrong, my dear loved? This is pretty bad. How could this happen to me? I'm programming so much. Shouldn't happen too often. Okay, here we have it. We have this function, and what you do now is you call the plot function, but instead of giving here plastic strain, you give it this evaluation function, and at the same time you can choose now the time step again for 0. And it is loading, but here we are. This is undeformed state time step 0, and our own evaluation function was used. And with this evaluation function, I showed you this, you can plot it at any time step with any results which are embedded, even with history variables and stuff like that. So it's really cool and awesome. I like it really much. Okay, so far this is a short introduction of my library. There's still a lot of stuff I could show you, but find it out yourself. I think it's more than enough for the beginning.